Comparing B-Trees and LSM-Trees. Even though BTree implementations are generally more mature than LSM-Tree implementations, LSM-Trees are also interesting due to their performance characteristics. As a rule of thumb, LSM-Trees are typically faster for writes, whereas BTrees are thought to be faster for reads. Reads are typically slower on LSM-Trees because they have to check several different data structures and SS tables at different stages of compaction. However, benchmarks are often inconclusive and sensitive to details of the workload. You need to test systems with your particular workload in order to make a valid comparison. In this section, we will briefly discuss a few things that are worth considering when measuring the performance of a storage engine. A BTree index must write every piece of data at least twice, once to the write-ahead log, and once to the tree page itself, and perhaps again as pages are split. There is also overhead from having to write an entire page at a time, even if only a few bytes in that page changed. Some storage engines even overwrite the same page twice in order to avoid ending up with a partially updated page in the event of a power failure. Log-structured indexes also rewrite data multiple times due to repeated compaction and merging of SS tables. This affects one write to the database, resulting in multiple writes to the disk over the course of the database's lifetime, is known as write amplification. It is of particular concern on SSDs, which can only overwrite blocks a limited number of times before wearing out. In write-heavy applications, the performance bottleneck might be the rate at which the database can write to disk. In this case, write amplification has a direct performance cost. The more that a storage engine writes to disk, the fewer writes per second it can handle within the available disk bandwidth. Moreover, LSM-Trees are typically able to sustain higher write throughput than BTrees, partly because they sometimes have lower write amplification, although this depends on the storage engine configuration and workload, and partly because they sequentially write compact SS table files rather than having to overwrite several pages in the tree. This difference is particularly important on magnetic hard drives, where sequential writes are much faster than random writes. LSM-Trees can be compressed better, and thus often produce smaller files on disk than BTrees. BTree storage engines leave some disk space unused due to fragmentation. When a page is split or when a row cannot fit into an existing page, some space in a page remains unused. Since LSM-Trees are not page-oriented and periodically rewrite SS tables to remove fragmentation, they have lower storage overheads, especially when using leveled compaction. On many SSDs, the firmware internally uses a log-structured algorithm to turn random writes into sequential writes on the underlying storage chips, so the impact of the storage engine's write pattern is less pronounced. However, lower write amplification and reduced fragmentation are still advantageous on SSDs. Representing data more compactly allows more read and write requests within the available I/O bandwidth. A downside of log-structured storage is that the compaction process can sometimes interfere with the performance of ongoing reads and writes. Even though storage engines try to perform compaction incrementally and without affecting concurrent access, disks have limited resources, so it can easily happen that a request needs to wait while the disk finishes an expensive compaction operation. The impact on throughput and average response time is usually small, but at higher percentile, see describing performance on page 13. The response time of queries to log-structured storage engines can sometimes be quite high, and BTrees can be more predictable. Another issue with compaction arises at high write throughput. The disk's finite write bandwidth needs to be shared between the initial write logging and flushing amenable to disk and the compaction threads running in the background. When writing to an empty database, the full disk bandwidth can be used for the initial write, but the bigger the database gets, the more disk bandwidth is required for compaction. If write throughput is high and compaction is not configured carefully, it can happen that compaction cannot keep up with the rate of incoming writes. In this case, the number of unmerged segments on disk keeps growing until you run out of disk space, and reads also slow down because they need to check more segment files. Typically, SS table-based storage engines do not throttle the rate of incoming writes, even if compaction cannot keep up, so you need explicit monitoring to detect the situation. An advantage of BTrees is that each key exists in exactly one place in the index, whereas a log-structured storage engine may have multiple copies of the same key in different segments. This aspect makes BTrees attractive in databases that want to offer strong transactional semantics. In many relational databases, transaction isolation is implemented using locks on ranges of keys, and in a BTree index, those locks can be directly attached to the tree. In Chapter 7 we will discuss this point in more detail. B-trees are very ingrained in the architecture of databases and provide consistently good performance for many workloads, so it's unlikely that they will go away anytime soon. In new data stores, law of structured indexes are becoming increasingly popular. There is no quick and easy rule for determining which type of storage engine is better for your use case, so it is worth testing empirically. Other indexing structures. So far we have only discussed key-value indexes, which are like a primary key index in the relational model. A primary key uniquely identifies one row in a relational table, or one document in a document database, or one vertex in a graph database. Other records in the database can refer to that row/document/vertex by its primary key or ID, and the index is used to resolve such references. It is also very common to have secondary indexes. In relational databases, you can create several secondary indexes on the same table using the create index command, and they are often crucial for performing joins efficiently. For example, in Figure 2-1 in Chapter 2 you would most likely have a secondary index on the user ID columns, so that you can find all the rows belonging to the same user in each of the tables. A secondary index can easily be constructed from a key-value index. The main difference is that keys are not unique, i.e. there might be many rows documents, vertices with the same key. This can be solved in two ways, either by making each value in the index a list of matching row identifiers like a postings list in a full-text index, or by making each key unique by appending a row identifier to it. Either way, both B-trees and log-structured indexes can be used as secondary indexes. The key in an index is the thing that queries search for, but the value can be one of two things. It could be the actual row document, vertex in question, or it could be a reference to the row stored elsewhere. In the latter case, the place where rows are stored is known as a heap file, and it stores data in no particular order. It may be append only, or it may keep track of deleted rows in order to overwrite them with new data later. The heap file approach is common because it avoids duplicating data when multiple secondary indexes are present. Each index just references a location in a heap file, and the actual data is kept in one place. When updating a value without changing the key, the heap file approach can be quite efficient. The record can be overwritten in place, provided that the new value is not larger than the old value. The situation is more complicated if the new value is larger, as it probably needs to be moved to a new location in the heap, where there is enough space. In that case, either all indexes need to be updated to point at the new heap location of the record, or a forwarding pointer is left behind in the old heap location. In some situations, the extra hop from the index to the heap file is too much of a performance penalty for reads, so it can be desirable to store the indexed row directly within an index. This is known as a clustered index. For example, in MySQL's InnoDB storage engine, the primary key of a table is always a clustered index, and secondary indexes refer to the primary key rather than a heap file location. In SQL Server, you can specify one clustered index per table. A compromise between a clustered index storing all row data within the index and a non-clustered index storing only references to the data within the index is known as a covering index or index with included columns, which stores some of a table's columns within the index. This allows some queries to be answered by using the index alone, in which case, the index is said to cover the query. As with any kind of duplication of data, clustered and covering indexes can speed up reads, but they require additional storage and can add overhead on writes. Databases also need to go to additional effort to enforce transactional guarantees, because applications should not see inconsistencies due to the duplication. Multi-column indexes. The indexes discussed so far only map a single key to a value. That is not sufficient if we need to query multiple columns of a table or multiple fields in a document simultaneously. The most common type of multi-column index is called a concatenated index, which simply combines several fields into one key by appending one column to another. The index definition specifies in which order the fields are concatenated. This is like an old-fashioned paper phone book, which provides an index from last name, first name to phone number. Due to the sort order, the index can be used to find all the people with a particular last name, or all the people with a particular last name first name combination. However, the index is useless if you want to find all the people with a particular first name. Multidimensional indexes are a more general way of querying several columns at once, which is particularly important for geospatial data. For example, a restaurant search website may have a database containing the latitude and longitude of each restaurant. When a user is looking at the restaurants on a map, The website needs to search for all the restaurants within the rectangular map area that the user is currently viewing. This requires a two-dimensional range query like the following. A standard BTree or LSM-Tree index is not able to answer that kind of query efficiently. It can give you either all the restaurants in a range of latitudes but at any longitude, or all the restaurants in a range of longitudes, but anywhere between the North and South Poles, but not both simultaneously. One option is to translate a two-dimensional location into a single number using a space-filling curve, and then to use a regular BTree index. More commonly, specialized spatial indexes such as R-trees are used. For example, PostGIS implements geospatial indexes as R-trees using PostgreSQL's generalized search tree indexing facility. We don't have space to describe R-trees in detail here, but there is plenty of literature on them. An interesting idea is that multi-dimensional indexes are not just for geographic locations. For example, on an e-commerce website you could use a three-dimensional index on the dimensions red, green, blue to search for products in a certain range of colors, or in a database of weather observations you could have a two-dimensional index on date, temperature, in order to efficiently search for all the observations during the year 2013 where the temperature was between 25 and 30. With a one-dimensional index, you would have to either scan over all the records from 2013 regardless of temperature and then filter them by temperature, or vice versa. A 2D index could narrow down by timestamp and temperature simultaneously. This technique is used by hyperdex. All the indexes discussed so far assume that you have exact data and allow you to query for exact values of a key, or a range of values of a key with a sort order. What they don't allow you to do is search for similar keys, such as misspelled words. Such fuzzy querying requires different techniques. For example, full-text search engines commonly allow a search for one word to be expanded to include synonyms of the word, to ignore grammatical variations of words, and to search for occurrences of words near each other in the same document, and support various other features that depend on linguistic analysis of the text. To cope with typos in documents or queries, Lucene is able to search text for words within a certain edit distance. An edit distance of 1 means that one letter has been added, removed, or replaced. As mentioned in making an LSM tree out of SS tables on page 78, Lucene uses a SS table-like structure for its term dictionary. This structure requires a small in-memory index that tells queries at which offset in the sorted file they need to look for a key. In level DB, this in-memory index is a sparse collection of some of the keys, but in Lucene, the in-memory index is a finite state automaton over the characters in the keys, similar to a trie. This automaton can be transformed into a Levenstein automaton, which supports efficient search for words within a given edit distance. Other fuzzy search techniques go in the direction of document classification and machine learning. See an information retrieval textbook for more detail, e.g. 40. The data structures discussed so far in this chapter have all been answers to the limitations of disks. Compared to main memory, disks are awkward to deal with. With both magnetic disks and SSDs, data on disk needs to be laid out carefully if you want good performance on reads and writes. However, we tolerate this awkwardness because disks have two significant advantages. They are durable, their contents are not lost if the power is turned off, and they have a lower cost per gigabyte than RAM. As RAM becomes cheaper, the cost per gigabyte argument is eroded. Many datasets are simply not that big, so it's quite feasible to keep them entirely in memory, potentially distributed across several machines. This has led to the development of in-memory databases. Some in-memory key value stores, such as Memcached, are intended for caching use only, where it's acceptable for data to be lost if a machine is restarted. But other in-memory databases aim for durability, which can be achieved with special hardware such as battery-powered RAM, by writing a log of changes to disk, by writing periodic snapshots to disk, or by replicating the in-memory state to other machines. When an in-memory database is restarted, it needs to reload its state, either from disk or over the network from a replica unless special hardware is used. Despite writing to disk, it's still an in-memory database, because the disk is merely used as an append-only log for durability, and reads are served entirely from memory. Writing to disk also has operational advantages. Files on disk can easily be backed up, inspected, and analyzed by external utilities. Products such as VoltDB, MemSQL, and Oracle x10 are in-memory databases with a relational model, and the vendors claim that they can offer big performance improvements by removing all the overheads associated with managing on-disk data structures. Our RAM Cloud is an open source, in-memory key value store with durability using a log-structured approach for the data in memory as well as the data on disk. Redis and Couchbase provide weak durability by writing to disk asynchronously. Counterintuitively, the performance advantage of in-memory databases is not due to the fact that they don't need to read from disk. Even a disk-based storage engine may never need to read from disk if you have enough memory, because the operating system caches recently used disk blocks in memory anyway. Rather, they can be faster because they can avoid the overheads of encoding in-memory data structures in a form that can be written to disk. Besides performance, another interesting area for in-memory databases is providing data models that are difficult to implement with disk-based indexes. For example, Redis offers a database-like interface to various data structures such as priority queues and sets. Because it keeps all data in memory, its implementation is comparatively simple. Recent research indicates that an in-memory database architecture could be extended to support datasets larger than the available memory, without bringing back the overheads of a disk-centric architecture. The so-called anti-caching approach works by evicting the least recently used data from memory to disk when there is not enough memory, and loading it back into memory when it is accessed again in the future. This is similar to what operating systems do with virtual memory and swap files, but the database can manage memory more efficiently than the OS, as it can work at the granularity of individual records rather than entire memory pages. This approach still requires indexes to fit entirely in memory, though like the Bitcask example at the beginning of the chapter. Further changes to storage engine design will probably be needed if non-volatile memory and VM technologies become more widely adopted. At present, this is a new area of research, but it is worth keeping an eye on in the future.